dash 2. As impressed as you are with the derivative at this point, you shouldn't be that impressed with the derivative. It's like, it's a lot of work. You're telling me the basis of math for the last century that made all the difference in the world takes all those steps? The answer is yes. But check this out. You don't have to do all this. I'm going to do all this. In fact, you don't have to do any copying for a while, okay? Only if I write on this page. I'm going to go off, every time I got to do one, I'm going to go off on a separate page. You don't got to copy all that stuff down. Now, if after I'm done, you're like, oh, I'm not very good at those, then you might want to go to the video and get good at these, all right? You don't have to be as fast as me. I've done these 1,000 million times. They go fast. It says, okay, use the definition of the derivative. So I'm about to use what's called the definition of the derivative to do these. And if that freaks you out, well, it shouldn't, because definition of the derivative is what you've seen already as the definition of the derivative. But I'm just going to highlight that. Use the definition of the derivative to differentiate each of the following functions. Apparently, after I find the derivative of this one, and this one, something's going to happen. All right? That's the whole goal. So the first one's f at x equals 7. Here I go, onto my separate page that I've made here, which you don't have to copy down, unless later you're like, I need those. Yeah? But don't do it. Don't focus on it. The focus of the lesson is right here. F at x equals 7. Okay, where we go? F at x equals 7. And the definition of the derivative says, if you want to find the derivative of a function, you go limit as h approaches 0 of f at x plus h minus f at x over h. That's the plan for finding derivatives. Now, this function is f at x equals 7. When I sub in x plus h into this function, I get a value of 7. This function has value 7. You're like, what if I sub in x plus h? The function's like 7. You're like, well, what if I plug in x? And the function goes, I'm 7. The value is, I am Groot. It's 7 every time, 7. So this is easier than the derivative questions you were doing. 0 over h. Well, 0 over h is 0. Answer 0. The derivative of the function 7 is 0. What does the function look like? F at x equals 7. It's just a horizontal line. Its derivative is 0. Of course it's 0. Yeah? Okay. Do another one. F at x equals negative 10. Same thing. Got to do it smaller if I'm going to fit these in. F at x equals negative 10. Here's the definition of the derivative. Limit as h approaches 0. F at x plus h minus f at x over h equals limit as h approaches 0. Sub in x plus h into the function. Negative 10. Sub in x to the function. It's always negative 10. And negative 10 subtract negative 10 is 0. I get 0 as the derivative of negative 10. Hopefully you're not that surprised by that. Derivative of negative 10, 0. Ooh, pi. Now, pi gets mysterious sometimes because it looks like it's a Greek symbol. You know, I think it's a variable or something like that. But pi is just 3.14. The derivative, like f at x equals 3.14 is just a line across at 3.14159. So there's nothing special about pi, really. Okay, so f at x equals pi. Here's the definition of the derivative. I'm trying to say this over and over again so you're not surprised when the homework or a test says definition of the derivative now. Definition of the derivative is just m tangent that we've been using. Limit as h approaches 0. F at x plus h minus f at x over h. Here, when you sub in x plus h, you get pi. When you sub in x, you get pi. The derivative of pi is 0. We're ready for our first rule of the day. You might be ready for the first rule of the day. The first rule of the day says, hey, if you've got a constant function, whether it's at 7, negative 10, pi, it doesn't matter where it is, this derivative is always going to be 0. I don't have to go through all that definition of the derivative stuff anymore. From now on, if f at x equals c for some constant number, whatever it is, then f prime at x equals 0. There's your first shortcut. You're unimpressed at this point. You're like, well, that's nice. So if the function happens to be a constant number, good. I can just write down derivative 0. I don't think that comes up that often. But hey, It's our first one of the day. Any questions about the constant function rule? On to the next section. It says do x squared, and x cubed. I've got them memorized. X squared, x cubed. I'm going to go over to the other page. I'm going to do all three of those right in a row and then come back with their derivatives, okay? If halfway through this you're like, do I have to memorize every single one? Oh no. Oh no, it's way better than that. Okay, so f at x equals x. F prime at x will be limit h approaches 0. F at x plus h minus f at x over h. I got to sub in x plus h to the function. I get x plus h. I got to sub in x to the function. I get x. The x's cancel. If you've done a few of these, you know, okay, everything that doesn't have h is going to cancel. And I get limit as h approaches 0 of 1. The answer here is 1. The derivative of x is 1. If you're really with me, you already knew that was coming. What's the slope of the line y equals x? 1. It's always 1. All right? Like, so what, I can just memorize that now? Well, yeah, you can. But don't make any grand conclusions just yet. I'm going to go after simple x squared now. F at x equals x squared. And I saw in the test, when I put an x squared up there, that for most people that expansion of x plus h went pretty quick. I hope, as I promised, was that after you do it a few times, expanding x plus h squared is not that difficult. And many of you weren't even showing your work because you were so good at it. And I'm not going to show my work there either. I'm going to say, hey, when you expand x plus h squared, you get x squared plus 2xh plus h squared. The x squareds go. How nice is that? I don't know why I've got an extra 0 in there. Let me just fix that up. Goodbye. Limit h approaches 0. 2xh plus h squared all over h. Some of you are common factoring that h and then canceling, which I love. Some of you at this point are just dividing the h. Some of you are making a big hairy mess. I marked it right, but you just do a whole bunch of stuff which I can't even read, and then you get the right answer out of there. So try and be a little bit better about cleaning this up. One thing that you're not doing is putting brackets around this. The h cancels out of each of those. This has to stay in a bracket after those h's have canceled, because we're saying limit as h approaches 0 of all that. I get an answer of 2x. So if I want the derivative of x squared at any particular value, it's always going to be 2 times whatever the x value is there. Nice and simple. And if you're jumping ahead in your brain going, well, so I got to memorize that? The derivative of x squared is 2x? No. Just stay in your seat for a second. All right? Now it says go after x cubed. Now, on the Unit 3 test, I put an x squared, as I sort of implied I would. I put an 1 over x, so it was like a 3 over x or something like that, as I sort of promised I did. And I didn't put the x cubed one on the Unit 3 test, or on the Unit 2 test. It's still available to me for the next chapter, you see? Now's when you get your little pink flapper out and you go, geez, he sure seemed to lean on x cubed a lot there. Yeah, so I'm going to go through x cubed very carefully here to make sure you know exactly how to handle x cubed. That's not going to be enough space. You need to f at x equals x cubed. F prime at x equals limit h approaches 0, f at x plus h minus f at x over h. Limit h approaches 0. Here it comes. X plus h cubed minus x cubed over h. How do I handle it when I've got a cubic? I don't like rewriting these lines every step of the way. I go over here and go, okay, just give me a second here. X plus h cubed, that would be x plus h times x plus h times x plus h. Expand this out, x squared plus xh plus h squared times an x. Oops, I missed one. Sorry, I was showing the whole expansion there, not the shortcut. plus xh plus h squared, all times x plus h. Collect up. Maybe you're a little faster at this because you know your expansion of x plus h. Maybe you jump right to this line here, and then you got one more expansion to go when you got a cubic one. So carefully. X cubed, x squared h, plus 2x squared h, plus 2xh squared, plus another xh squared, plus an h cubed. One check you can do is, hey, if I'm multiplying three things in a bracket by 2, I should be getting 6 terms. 1, 2, 3, 4, 5, 6. I'm going to collect them in here, though. That was just side work I was doing there. I got x cubed plus 3x squared h plus 3xh squared plus h cubed minus the x cubes. Where's the data management people? Well, you did a little bit of this in grade 11. Look at 1, 3, 3, 1. Yeah, a little Pascal's triangle poking its head up there. You don't really need to know all that right here, but it actually is helpful for the proofs of this to bring a little data management into this. Do good things happen? X cubed goes with x cubed. And some of you are doing this all in one line now. You go, oh, look, the h divides into everything that's left. So I'm limit as h approaches 0. You should be using a bracket here. I put a red line for brackets around everybody who forgot the brackets, but I didn't take a mark off. So watch out for those red lines on your test. Like, hey, really, you could lose a mark here, so let's just tidy this up a little bit. Divide them all by h. 3x squared plus 3xh plus h squared. 3x squared. 3xh, h squared. Now I can sub in h equals 0, and I get my answer of 3x squared. Apparently, if you want to find the slope of x cubed anywhere, you just go 3 times whatever x value you have squared, and that'll give you the derivative. Apparently, it's that simple. Any questions about that derivation there, so that you know that if it happened to come up as the x cubed question, or as the derivative question, from first principles on a test? Back to you. And it says, what's the rule? You're like, what's the rule? The rule really looks like I'm going to have to memorize all this crap. I'm not going to do x fourth in the board because it spooks people out when I do it. It makes people ask questions like, is that going to be on the test? And no, it's not. But I'm going to put x fourth up here to try to help you to see the rule. The derivative of x to the fourth is 4x cubed. I'm going to do one more thing to try and help you see what the rule is. I'm going to say, okay, well, this is what the grade 9s are working on right now. One girl was very upset that we kept putting exponent 1 on these things. She says, well, if there's supposed to be exponent 1, why didn't we have exponent 1 on it the whole time? Like, well, we really did, actually. It was always exponent 1. We just never wrote it before. It's tough to teach little kids to count if they have to say 1 to the exponent 1, 2 to the exponent 1, 3 to the exponent 1 all the time. So we just leave it up. And then, one last thing. This is 1, but now there's no x's. Now look at, oh, one more to go. Where's the other one I got to fix? There's x with exponent 1. Now take a look at that and see if you can see what's going on. And if you see it, and you're like, it can't be. Yeah, it really can. It is as good as it looks. Who wants to put it into words? What the heck is going on with these things? Will? He's all over it. That's exactly what I'm going to write in just a second. Can someone use words instead to describe what's happening here? Say someone was away and you wanted to describe what you do there. The fancy rule is the best way to memorize it. However, what's actually happening? Yeah, you bring the exponent out front and you subtract 1 from the exponent. You're like, after all this, after all those tables, 2 to 2.1, 2 to 2.01, after limit as h approaches 0 f at x plus h f at x, after all that, you're telling me we came all this way to come up with a simple pattern that I think it's possible the grade 8s would recognize. Like they'd look at the pattern and go, I see the pattern. I see what you have to do here. And the answer is, yeah, we came all that way to do that. It's beautiful. Rule. If f at x equals x to the power of n, then f prime at x will be nx to the n minus 1. You can memorize it that way, or you can memorize the way Brad said, which is just like, hey, you bring the exponent down, you subtract the exponent by 1. By the end of day today, I don't know if in this period, I'll throw up a proof of it so you can get an idea that this isn't just, oh, it's sort of happening. Mr. Todd sort of pointed towards it, like a formal proof that shows that it's actually true. Any questions about that? Well, there should be a question. Your question should be, okay, so on the next test, x cubed pops up. Which way do I do? Do I do this? Or do I do this? Because you're really hoping I'm going to say this, right? And the answer is, on all the questions on the test, you do this. This is what we're doing this chapter, except one. There's one question that's going to say, from first principles, from the definition of the derivative, show that you know how to do this certain derivative. So I'm going to pick one at random for you to do. Okay? So you got to show that once more in this chapter. The rest of the time, we moved on. We're power rule. This is what it's called, the power rule people from here on in. More time here? Okay, constant multiple rule. I'm not going to go through the individual proofs of these individual things. Consider them a good exercise. If you watch those proofs I did over here, and you're like, yeah, I got that. And it certainly seemed like you did, because most people did pretty well on this in the test. If you're like, I got that, then yeah, make sure you're practiced up and polished up on these come test time for whatever combination is going to come at you. But if you're like, yeah, I got that totally, you know, like, give me new stuff, okay? Because I can do the derivative from definition of derivative. Here's the way these derivatives come out. If you do derivative of 2x, you get 2. Derivative of 3x squared, you get 6x. And if you do the derivative of negative 5x cubed, you get negative 15x squared. We need to expand our power rule a little bit. It's really just the tiniest bit. You're waiting for the other shoe to drop, and the other shoe does drop in this lesson. Things do heat up, and I'll warn you. Right? As soon as I put the question up on the board, I'll go, ooh, things just heated up. But it's not here. It's what you would hope for. How do we have to change? This one's the easiest one to talk about, even though it's the most complicated function. How do we have to change what we just said to deal with a constant multiplier out front? Because a second ago we said, okay, bring this 3 down and reduce it by 1. That's sort of happening, but there's one more little thing we've got to keep in mind when we're doing that. Veronica? Yeah, so if you've got something coming down that you're going to multiply by, and there's already something there, you just multiply the two values. So here it is formally. If f at x equals a x to the n, then f prime at x equals na x to the n minus 1. So it's still the same. You just might have a multiplier up front that you got to multiply. That easy. Sum and different rules. There's not much to talk about here. Hey, let's try them. Let's take the derivative, the power rule for a test drive. What's the derivative of x squared? Think about it in your head. What? 2x. What's the derivative of 9x? Okay, the derivative of x was 1. The derivative of 2x was 2. 9. And the sum and difference rules are just saying what we would hope is true. Really, underneath all of this, the limits are still going on. We've just got a shortcut. So the limit rules still do apply, which means if you want to take the derivative of two things added together or subtracted, you just take the derivative of each one and just add or subtract them together. Like it's nice. Like everything that happens for a few sections here, it's like it's been so hard since we started learning 2 to 2.1, 2 to 2.01, and suddenly for part of a lesson here, it's like, oh, this is pretty nice. Take a look at those and make sure you agree with those three. It's a little complicated the way I'm going to write this. If f at x equals g at x plus or minus h at x, for instance, several functions added or subtracted together. If you want to find the derivative, it's no big deal. Take the derivative of the first one, whatever it is, and then add or subtract the derivative of the second one. Just take the derivative of the individual pieces. Keep the adds and subtracts where they were. If that rule makes it confuse you at all, just go back to the examples and say, all we're saying is, go ahead and take the derivative of the individual pieces. The add or subtract can stay in between. Okay, but any questions on these three derivatives? About how I came up with the numbers? Okay, one curveball then. What happened to the minus 4? Its derivative was 0, so it's not on the list there. Yeah, okay. Questions about those? Let me rewind and attack that like this. The derivative of, and I'm going to get rid of this x to 0 now. The derivative of x, find the slope of the function y equals x. What's its slope? It's always 1. I did that algebraically, but that one particularly is one that I don't know if we needed all of this to do that. What's the slope of the line y equals x? Well, it's 1. It's always 1. So if I went to 2x, its slope is always 2. I went to 3x, its slope is always 3. I mean, I can prove it algebraically, and I think I did in this lesson, but I don't know if you need that. Derivative of 9x? It's a line 9x. Its slope is 9, you know? Okay. Other questions? "13 examples and I'm done." But some are faster than others. You're going to find this homework is like, some of the questions are like, bang, done. But there is some that have a little torque to them, so let's just walk through these. Use these previous examples to find these derivatives. F prime and x. The derivative of, and I'm trying to be funny here to make sure you're right with me. What's the derivative of 25,412.85? 0. Having trouble visualizing that? What does the line y equals 2 look like? This. Y equals 10 looks like this. Y equals 25,000. It's way up here, but it's just a horizontal line. What's the slope? 0. Okay. Maria, this one's for you. Derivative of 17x. Just 17, yeah? If you want, it's actually 17 times 1. Because the derivative of x is 1. Yeah? But I don't know that that's how people think about it. Here's the first seemingly tough one. Can you imagine if I asked this question half an hour ago? X to the 7, x plus h, x plus h, x plus h, x plus h, do. We'd need the data people. The data people would jump right in and go, no problem. Data people, what would you do? You go like this. Or you do your chooses or whatever like that. So, you know, like, it's not impossible to do these expansions. But the way we've been doing them, x to the 7th would be a big problem. However, now with the power rule derivative ready to rock and roll here, what's the derivative of x to the 7th? I'm giving you all time to think because I don't want to fly by here. I realized time-wise I do have enough time before lunch to finish this off. I want you to have time to access this. Think of it in your brain, what you think the answer is, and then hear what the answer is. 7x to the 6th. It feels like cheating after all this math. Like, I know these questions, you're like, really, that's it? That's all you gotta do? Yeah, really. Yeah. Proofs, that's why I might need up to lunch. I gotta show you some proofs anyways. Okay, what if there's a coefficient out there? Ooh, now it gets tough. There's a 12 out there. What's the derivative of 12 x cubed, Josiah? 36x squared. Let me just add, he's right. Let me just ask some silly questions. Where'd the 3 go? Yeah, so it's a multiplier that you're bringing down. If there happens to be something there, then you just multiply by what is already there. Most people do it in one step. If I were to write it out separately and write 3 times 12x squared, it loses some of its beauty, but also it loses some of its clarity, I think. This is clearer. x to the negative 9. Okay, so this is the moment, eh? This is the moment where this lesson sort of changes a little bit, because up till then you might have been like, oh, so this is going to be so easy. I'm going to be done this homework in like 2.5 seconds. And then we go, oh yeah? Want to play, huh? It's unbelievable the power we have now. Keep in mind, on the test, 1 over x caused some headaches to find its derivative. 1 over x to the 9th. Geez, it's like all day you're going to spend trying to do 1 over x to the 9th. The old way. But now, really think about this, because this is the one that needs some thought. You got to really think about what the rule said to do. Will. He said negative 9 over x to the 10. I'm going to do it this way first and do this step in between, because that follows the exact rule I said, which is bring the number down out front, negative 9, and then reduce the power by 1. Reducing negative 9 by 1 goes down to negative 10. He's right, though, for reasons that will finally become clear tomorrow. We don't like negative exponents, and tomorrow it will become very clear why we don't like negative exponents. Up until now, it's just been a rule your teachers told you. Oh, we don't like negative exponents. Please don't use negative exponents. You're like, why? What do we care? Tomorrow you find out why we care. So we're going to make an effort to write our answer with positive exponents. As a quick refresher, it's just that simple. Negative exponents means this was a positive exponent, but it should have been in the denominator. So you move it down to the denominator. Oh, now it's ramping up. Well, I put 2 lines there. I'll put 4 lines there. Things just ramped up again. Negative 3 over x squared. Okay. And then you stop and you're like, this doesn't look like the other ones. All the other ones were x to the something. We've got a rule for x to the something. Bring down the power, reduce it by 1. This isn't x to the something. What can somebody do something to this to get it back to x to the something? Brad. Yeah, so this is the section of calculus, the next 2 weeks, where you're like all these little lessons all the way along the way that were just annoying little lessons along the way about negative exponents and fraction exponents and all this stuff that just seemed like teachers were torturing you. It was all getting ready for this moment. I don't know if you saw the original Karate Kid. He learned to wax the car and paint the fence and all this kind of. And then there's this moment where he finds out, he's like, oh, I can do all this stuff. These lessons are where it is. Like all this stuff you learned all the way through high school matters now. I'm not taking the derivative here. I'm just rewriting this in a form that is derivative friendly. Derivatives like negative exponents. They do. So this is the whole thing. Teachers are like, oh, don't use negative exponents. The derivative says, oh, hang on. The derivative's like, I like negative exponents. So when you're going to take the derivative, go with the negative exponent. When you're done with the derivative, get away from negative exponent. Why? Tomorrow you'll see why it's so important. Now we're ready. F prime at x, 6x to the negative 3. I'm done with the derivative now. And then go back to positive exponent. And for one more day, just trust me that positive exponents is where you want to be. Questions? More time? Yeah. Look at those 3. Are these the last 3? Oh no, there's 2 more after that. Oh, it gets easier after that. Okay. Let's just rewind. At the end of number 4, it's like, oh, this is beautiful. As long as it's x to the something, it's just bang, bang, done. Even if there's a coefficient up there, don't care. As long as it's x to the something. Then we ran into negative exponents. We went, oh, now we might have to look and see, can I write it as x to the something? And we needed to deal with negative exponents. Now I've got root x. I'd like to write it as x to the something. Can root x be written as x to the something? And if yes, what is the something? X to the 1/2. See, one of 2 things is either happening. You're like, oh, the stuff that they were jamming in my brain is finally coming and make it mattering. Or you're like, I didn't jam any of that stuff in my brain. That's a bit of a problem. And then you're getting your red highlighter out, and you're highlighting these going, I didn't see that coming. And I could have sat here for an hour looking at root x, and I wouldn't have known it was x to the 1/2. Well, now's the time. Red highlight that, get the little sticky note out and go, okay, good to know. Got to have that one in my bag of tricks for the next little while. Root x is x to the 1/2. Now we're ready to go, but this one's just a little more trouble. Bring down the exponent. That's not so bad. Then reduce the exponent by 1. What's 1/2? Subtract 1. Just to be clear, the uncomfortable pause and eye contact is not to call you out. It's to encourage you to think and go, do I know the answer to this? Then when the answer comes out, you're able to decide. What should I do next? Did I know the answer or didn't I know the answer? What is 1/2 minus 1? Negative 1/2. I'm having a war with my microphone here. Negative 1/2. And now, over the next few days, we'll finally learn why this, for derivatives, is nice to write it like that. When we're not doing derivatives, we really want to go back to this. And I really encourage you to ask me a question if you're not sure what I did there. There's only two possibilities. You're like, oh, yeah, I get that. Or it's like, you're going to really need to tell me about what just happened there. Two things happened. The negative exponent said, okay, whatever you've got to put it in the denominator. So negative exponent says go to the denominator. The 1/2 says square root. So I did both at the same time. I said negative 1/2 means square root, yes, but negative means go back to the denominator. So the 1/2 is there, but this x to the negative 1/2 becomes into the denominator, but with a root. Oh, look at this guy. This is one thing, to know this one. But this is like, that's reaching deep down into your, chipping the rust off all your old knowledge about grade 11 exponents. Back to what we're trying to accomplish. We want it x to the something. We've got a rule for x to the something. We don't care what the x to the something is, as long as it's x to the something. How do I get this back to x to the something? X to the 4/3. So two possibilities again. You either saw that coming, or you're like, yeah, I sort of remember it's a fraction. Where does the 4 go? Where does the 3 go? In which case, yeah, got to brush that up. Or you looked at that one, no way am I ever going to get that back. In which case, that gets your red highlighter, your pink sticky note, and go, that's got to be in my bag of tricks now. I've got to bring that back up and in. The rest isn't so bad. Bring the 4/3 out and multiply by it. I think for most people, when they get 4/3 times 12, they're actually going to write it. They're going to go 4/3 times 12 and do it in another step. Some people will be able to do that fraction in their head right off the hop, and that's great. But here's a tough one, though. X to the what? 4/3 subtract 1. Josiah. Yeah, 1/3. How did you do it in your head? Different people do it differently in their head. Yeah, he thought in his head it's 1/1, which is 3/3. So I'm really 4/3 minus 3/3, which is 1/3. And so now I'm going to tidy this up. 4/3 of 12 would be 48/3. I got 16, and I got x to the 1/3. Not clear yet whether x to the 1/3 is fine. But we're going to find out that we're probably going to want to go back to this. The numbers up in the exponents, whether it's negatives, 1/2, whatever, are good for doing derivatives. When we actually go to solve questions, we're probably going to want them as roots. I'm not making a rule just yet. I'm just saying you should be prepared for that. Pi/6. Derivative of pi/6, Veronica? 0. Just threw that in there to try and spice things up a little bit. Pi/6 is just a number. 3.14 divided by 6, like 0.5 or something like that. It's just a constant function. Its derivative is 0. Why does my screen say there's 7 pages? There's not 7 pages, is there? There's 2 more pages. So there's 6 pages, okay? Well, there's some easy ones coming, some faster ones coming. More time here. Oh, look at this guy. Maybe the toughest question so far because there's a lot going on here. And you may feel that it's appropriately named. It's on the video now. You can get your parents. You can show that video to your parents. Like 8 over 3 root u. The plan is get this back to u to the something. What's the something if this is going to be u to the something? We won't always be able to do this, but we can here. Negative 1/2. Where does each of these pieces come from? It's negative because it was in the denominator. And it's 1/2 because it was a square root. You see all these rules are starting to come together. And then the 8/3 is just a coefficient. Now you can do your power rule. F prime at u. Negative 8 over 6. U to the Well, you can ask me questions about the negative 8 over 6 in a second. That's not the particularly hard part. This is now negative 1/2 minus 1. I'll have to record this lesson for the grade 9s because they're like, they're annoyed by fractions at this point because of all the little rules that are going on. I'm like, we need them. We need them for situations like this. Negative 1/2 subtract 1. How are you going to think about 1 to give yourself a shot here? 2 over 2. So negative 1 over 2, subtract another 2 over 2 is negative 3 over 2. Incidentally, those little things long-term don't become calculus students' problem. They do enough of these that they get used to those. So if those are like, ooh, got to brush off my fractions here, that'll come. It really will. I'll just improve this a little bit now. Okay, so far, reduced negative 8/6 to negative 4/3. Now this u to the negative 3/2, it's negative, so it's got to come down to the denominator. And so it becomes square root of u cubed in the denominator. The 2 becomes the root, the 3 is the power. Okay, but before you go, okay, you know, you're killing us here, Mr. Todd. For once, you taught a lesson which is like, okay, I got this. This is really good. Right about here, you're like, I like this. This is nice. And then you had to ramp it up to Pluto. You know, I take it right deep into outer space. Yeah, there's questions like that. But there's also questions like this. Where taking the derivative is pretty nice. Where you just as fast as you can write, you're writing down the answer, okay? So I don't want to take away from the beauty of this lesson, which is that the derivative is a beautiful thing. Oh, there's 2 more to go. Two more examples. Why did this take so long? And maybe a little bit of proofs before 11:35. Okay. Questions about that one? Sort of brought it back down to earth here, yeah? Lots of earth questions in this chapter too, or are you just taking the derivatives pretty straightforward? Pi x squared minus 2 root x. Okay, this is a little bit of work. Pi x squared is ready to take the derivative. It's fine the way it is, but 2 root x isn't. What should I would do with the root x to get it ready for taking the derivative? Well, yeah, this goes back to x to the 1/2. And then taking the derivative is not so bad. I'll pause there. It's too bad Fiona's not here because she'd definitely be deeply frowning at me at this point, I think. And she'd be saying something, or thinking something. Why did we go through all of this? Why didn't you show us this like last March? What kind of torturous, mean thing was that to do, to leave this on the shelf and bring that out at the last second? And there's several answers to that. One is, this thing is useless if you don't know what it is and what it does. You don't understand the power of it. But there's a better answer. You don't like that answer, you're like, oh, I don't care. You could have taught me what it does. Seriously. You're pretty good at explaining these things, Mr. Todd. Are you sure you couldn't have, in an afternoon, explained what this thing was and what it does without putting us through all that? This thing has a major limitation. What's the major limitation? Can you identify what the major limitation of this thing is? Brad. Yeah. It's a problem because it only handles a very, very small kind of function. X to the something. And we've seen a lot of other functions besides that. This thing will be of no help for sine, for cosine, for log, for ln, for 2 to the x. None of those things is it helpful at all. And anything complicated like this, it is completely useless. I'll give you some more weapons coming up, but just to show off the limitations of this thing is you're still stuck with having to be able to go and do a bunch of work to get ready to do the derivative, then take the derivative. So this weapon I've given you is incredible. It is incredible. It might be the most incredible thing you do in math in high school. But it's not Thanos. It's not omnipotent. It can't handle everything. You know, there are still some problems that it has that we have to deal with. And so don't get carried away with how awesome this thing is. Little shout out to Fiona there. I'm sure she's going to be watching this video over lunch hour. Questions though on that last example? I did it really quickly while I was talking. I hope this isn't too bad. You might have to FOIL something out before you apply your new power rule. More time? More time?